Dear colleagues, I'm glad to welcome you here at our online meeting at the third conference on optical reflectometry, metrology and sensing 2020. The conference is held by the Photonics Laboratory and Agri-Biophotonics Laboratory of the PEM Federal Research Center of the Ural branch of the Russian Academy of Sciences. The co-organizer of the conference is Povolzhsky State University of Telecommunications and Informatics, Samara, Russia. Unfortunately, this year we are unable to meet in person, but we do hope to make this event interesting. So, we are about to start the day of our conference. A couple of words about how it works. Some speakers go online and perform live presentations. Some speakers send video files, we show this, and just after that they connect for a discussion. The discussion may go in English as well as in Russian, depends on the exact case. Our scientific secretary, Dr. Yuri Konstantinov, is also here. Hello, Yuri.
Hi, Alisa. Thank you so much. Thank you for help, for assistance in announcing our talks. Dear colleagues, thank you for coming up, for joining our conference. Very nice to see you here. Dear colleagues, please send your questions for the speakers to the email you see on the screen. Just like Alisa said, we will have a discussion after the presentations, so please send your questions. Well, first, let's give the floor for some welcome words to Dr. Ivan Loboch. He is working with fiber lasers in Novosibirsk. He's developing lasers, fiber optic lasers for reflectometry applications. And we have a short video with him. Let's look.
Hello, dear colleagues. Glad to see you among participants of Optical Reflectometry Conference. If you watch this video, be sure the event has already started. It should be noted that despite the difficult world situation, the organizers united all like-minded persons, researchers in the field of reflectometry. We thank them so much for this. I want to thank all the participants who agreed to attend in such undiscovered conference format. Everything is once new and incomprehensible, so it wasn't time with the reflectometry. And now it is a standard and powerful tool in many fields of science and technology. Say metrology, remote analysis, sensing, and so on. But every one of you always finds something new in this field and ready to share this knowledge with your colleagues. I hope the new format of this event will be useful in the future, when the things got better. We decided to create the joint session of Optical Reflectometry 2020 with International Workshop on Fiber Lasers in Novosibirsk. It is difficult to imagine the reflectometry without a laser. We are looking forward for arranging such a big international event containing a number of conferences. As a part of the organizing committee, I wish you fruitful work at our events.
Well, thank you, Ivan. The next welcome word is from Dr. Raman Ponomaryov. He is from Perm State University and from Photonics Laboratory of Perm Scientific Center. He is developing the integrated optic circuits, and the frequency reflectometry is one of his famous instruments. Raman, are you here?
Hi Yuri, yes, I'm here, nice to see you. Yes, we are using optical frequency reflectometry for investigations of processes in integrated optical modulators. As you know, there is a lot of physical phenomena in the crystal lattice of lithium niobate, where we make waveguides for phase and intensity modulators for gyroscopy and telecommunications. Optical reflectometry helps us to observe mode interactions and mobile charge movements near the waveguide. It's very sensitive measurements which helps our researchers to make better our integrated optical circuits. Thank you.
Thank you, Raman. Yeah, so after the welcome words, we're about to start it. Let's begin.
My friends, we are about to start the invited talk. Please welcome Avishay Eyal. He is professor at School of Electrical Engineering, head of the Undergraduate program, Faculty of Engineering, Tel Aviv University, Tel Aviv, Israel. The talk topic is Sinusoidal frequency scan of OFDR.
Hello everyone, my name is Avishay Eyal. I'm from Tel Aviv University. Before I begin, I would like to thank the organizers for inviting me to give this talk. I was looking forward to this conference and also I was looking forward to visit the city of Perm and the research center there, but unfortunately due to the corona this did not happen. But hopefully one day after this nightmare ends, I will be able to pay a visit. So this is the title of my talk, Sinusoidal Frequency Scan OFDR. And OFDR, as I'm sure you all know, is Optical Frequency Domain Reflectometry. And I'm going to discuss, this is the outline, I'm going to discuss briefly about types of reflectometric systems, then in particular OFDR. And then I'll say a few words about issues with OFDR, and one of the main issues is the nonlinear scan, which corrupts the performance of OFDR. And then I'll introduce what we call sinusoidal frequency scan OFDR, or SFS OFDR. And then I'll talk about computational efficiency and show how we can make this method more efficient in terms of complexity or computational complexity. And then I'll summarize. So we are discussing reflectometric systems, of course, and in a reflectometric systems, we have the interrogator, which launches light into an optical fiber, a long optical fiber, and it detects the backscattered light, and according to the backscattered light, it enables detecting and measuring events that occur next to the sensing fiber. And there are various types of reflectometric systems. They can be divided into categories in different ways. Here I chose to divide them into what we call direct detection systems and coherent detection systems. In a direct detection, we have just an optical detector, and OTDR, optical time domain reflectometry, is one of the methods which in many cases uses merely direct detection. And of course we have systems which use coherent detection, and coherent detection uses a coherent receiver, and we have both a signal coming, optical signal coming into this receiver, and an optical reference. And in this family, we have the coherent OTDR, we have the coded OTDR, and also, of course, we have OFDR, optical frequency domain reflectometry. Now, what are the pros and cons of these methods. In the case of direct detections, the pros, the advantages is that we deal with a simple and affordable interrogator, and another important point is that it is less susceptible to phase noise. On the other hand, in direct detection systems, and in particular in OTDR, there is a stringent relation or limitation which affect its performance, and this is the trade-off between its spatial resolution and sensitivity. Since OTDR is based on pulses, the more resolution we would like to obtain, these pulses are going to be narrower, and this means that we launch less light into the fiber and we get worse in terms of SNR and less sensitivity. Another disadvantage is that it requires excellent extinction ratio, and often it only provides us with the amplitude of the backscattered response and not the phase. And here the issue is that this amplitude is not linearly related to external pressure or strain perturbations to the fiber, whereas the phase indeed is related in a linear manner to these external perturbations. So regarding the coherent detections, on the other hand, the pros or the advantages is that we can have very high spatial resolution, we can have high sensitivity, and it usually provides us with both amplitude and phase. The disadvantages of these methods is that they are much more susceptible to phase noise and phase nonlinearities, and they require, in order to process the raw data, they require more challenging signal processing. In the rest of this talk, I'm going to focus on the case of OFDR, Optical Frequency Domain Reflectometry, and also I'm going to focus on a particular disadvantage out of the disadvantages that OFDR has, one specific limitation, and this is the phase nonlinearities. I will discuss how these phase nonlinearities affect the performance of OFDR and how we can deal with these nonlinearities using our method, which is sinusoidal frequency scan. So a little bit about OFDR. So in the case of OFDR, this is a very simplistic and schematic presentation of optical frequency domain reflectometry. Essentially what we have is a swept source whose frequency varies linearly with time. nominally linearly with time. This is what we would like to have, but usually this is not the case, and I'm going to discuss it. And this light with the instantaneous linear frequency scan enters a splitter, and then we have a signal arm and a reference arm, and light which goes into the signal arm goes into the sensing fiber and gets backscattered, and then it propagates back to the receiver, and it is mixed with the reference and bits with the reference, so that we have a beating signal between the backscattered light and the reference. And one important parameter in the performance of OFDR is what we call the scan slope, gamma. How fast the frequency varies as a function of time. What is the rate of the frequency change? And another thing is that, as we will see in the coming slides, we need this gamma to be constant. We need it to be constant with time. Otherwise, this is going to affect our measurements adversely. It's going to affect the spatial resolution and introduce crosstalk, as we will see. So, as I said, in OFDR, the instantaneous frequency changes linearly with time, and this is a representation of that. We have here the instantaneous frequency as a function of time, and we have two graphs. One of them is the reference graph, and the other one is the signal which has propagated in the fiber. And in this particular graph here, in this schematic, I only introduced a single reflection from a point which is z meters away from the transmitter. And of course, in a realistic situation, we have a continuous reflections from the fiber, but here, just for sake of clarity, I only drew one reflection. So it is convenient to describe the performance of OFDR using what we call the spatial impulse response. So suppose that we have just a single reflector out of the entire sensing fiber. We have a single point reflector, and this point reflector the response due to a single point reflector is what we call the spatial impulse response. And typically it should look something like that, like the plot that I drew here. And of course that the width of this graph, of this peak, is what we call the spatial resolution of the method, in this particular case, the spatial resolution of OFDR. And now I want to talk about the issue of the nonlinear scan. So ideally we would like our interrogator to produce light with instantaneous frequency that look like a sawtooth, with perfect slopes, with constant slopes, and very rapid return to the zero frequency deviation. But Of course, in order to generate something like that, we need very high bandwidths, and usually the circuits that generates the scan, the frequency scan, have their own frequency response, and they slightly, or sometimes more than just slightly, modify the sawtooth into something which is corrupted, and which means that we, of course, here it's pretty exaggerated, but this means that we don't have a perfect sawtooth in the scan, and due to that, what we are going to see is the following effect. Now that we have, suppose this is the reference, and now we have something which is backscattered from a signal. What you can see here is that what originally was two parallel straight lines, which gave us the reference instantaneous frequency versus the backscattered instantaneous frequency. These are no longer straight lines, and the difference between them is no longer fixed. And this means that instead of having a single bit frequency associated with a given reflection, now we have a range of frequencies, which are being associated with a given point in the fiber, and this means that our spatial impulse response deteriorates, and it's no longer as nice as I showed you previously, but rather we will have something which looks like that in the plot here to the left. So we see that the spatial impulse response now is broadened, and of course this has a very bad effect on the performance of the system. And this brings me to what we call sinusoidal frequency scan. It is well known that to generate a sinusoidal signal rather than a linear sawtooth signal, generating a sinusoidal signal is much simpler, much easier, and therefore what we proposed is that instead of using a linear scan, we can use a sinusoidal frequency scan, and out of the period of this sinusoidal scan, we will try to look close to the range where the sinusoidal scan is linear, but essentially we do even more than that, because if we do focus just on the linear part of the sinusoidal scan, then it means that we lose part of the frequency range. And if we don't use the entire scan, the entire frequency range, it means that we are going to lose resolution, because the resolution in the case of OFDR is determined by the total frequency range which is being scanned. So the method that we proposed actually allows us to go even to a broader range, even though the frequency variation associated with a given reflection point in the fiber is no longer, or the instantaneous frequency difference is no longer fixed. Therefore, we have a range of frequencies, but still, according to, due to the special way in which we process the backscattered light, we are able to still obtain very good spatial resolution. So what is the idea? How do we perform the processing of the raw data, of the backscatter data? In order to understand that, I would like first to talk briefly on how we do it usually in the regular OFDR case. So in the regular conventional OFDR case, where we have a linear scan, it is well known that the processing is merely an FFT, a fast Fourier transform, or a DFT, of course, which are equivalent. We can write this in a form of, in a matrix form, just to get some insight regarding how this process actually works. And in order to perform DFT, in this representation, what we need to do is to take the measured signal and to multiply it by the DFT matrix. Now, if we look carefully, we can see that essentially we obtain the reflection profile. We obtain the reflection profile by doing all these projections. Essentially, we project the measured signal on the response expected from different positions in the fiber. So the lines in this matrix, in the DFT matrix, are essentially the expected response, expected backscatter from z equals 0, and then from z equal dz, and z equal 2dz, etc. And this is how we obtain the reflection profile. So in a very similar manner, we can implement what we call the sinusoidal frequency scan, SFS, OFDR analysis. And all that we have to do is replace the previous matrix, the DFT matrix, with another matrix. But again, the rows of this matrix are the expected signal from z equals 0, from z equals delta z, to delta z, etc. And this is how we get the reflection profile. So this can be done, of course, and we have implemented it, and we have tested it with in the work which is given here below. And here you can see some results from this work. These are experimental results, and you can see how, if we in these plots, you see the reflection from a point reflector, a discrete reflector, and you can see the result of the SFS processing that I described previously, the result as a function of z, and for different windows of processing. These percentages that you see there, the 5%, 7.5, and up to 20%, is how much do we take from the period of the scan, of the sinusoidal scan. We have to remember that if we take the maximum that we can take is half a period, which is of course 50%. And here what we show is how we take up to 20%. And we have to remember that as we take more and more out of the sinusoidal period, it means that we are less and less linear, and this makes the processing more challenging. But you can see that when we increase the processing window, we get better and better resolution. And this is, of course, encouraging. Here you can see in a different representation the full width half max in meters as a function of, again, this percentage out of the entire period, and our measured points and simulation. And what you can see essentially is that the measurement really fits very well the simulation. But also you can see that the simulated OFDR and the simulated SFS OFDR really gives almost identical performance, which means that we can use SFS OFDR and get the same performance as we expect from a theoretical perfect OFDR. But the use of SFS or OFDR is easier due to the fact that we need to scan sinusoidally rather than linearly. But there is still an issue, which this issue is with regards to the computational complexity. Of course, in order to process OFDR in the conventional manner, we can use the FFT, the fast Fourier transform, which of course we know has excellent computational efficiency. But up to now, according to what I described to you, we should expect that the computational complexity of the SFS OFDR is going to be not very good, because we need to do this matrix multiplication, which is the matrix has a dimensions of n squared, where n is the number of points, of resolution points. So we expect not very good computational efficiency, which means that in its current form, this method may not be ideal for real-time implementation, and this is something we would like to have, real-time implementation. So can we devise another way to process SFS OFDR? The answer is yes, and this brings me to what we call fast SFS. And I'll describe it, but I'm not going to get too much into the details. I would show you the equations, but I will do it rather briefly, and I suggest that whoever of you is interested, I'll give the reference where you can find the details of the fast SFS. So essentially, if we look at this matrix representation that I gave you previously, we can write it in a continuous form in the following manner. So we see here rho tilde is the profile, the measured profile that we would like to obtain, where V of t is the measured signal. This is the detector output essentially, and this exponential term is essentially what we expect to see if we if we look at a single reflection from a point whose total delay is tau. And tau, of course, is related to z. So within this parameter tau, or variable tau, we have z within this parameter. So we need to implement this, this integral. We can write it slightly in a different manner and introduce WT, which is the window of processing, and then write it with an integral which goes between minus infinity to infinity. And another thing that we have done here is to separate the exponential into two terms. One of them depends on t alone, and the other one depends on t minus tau. And this can also be written in a digitized version. Of course, when we do the measurement in the lab, we have all these variables. We have them in their discrete form, and we have Zm, where Zm are the points along the fiber, and we have Tn, which are the temporal sampling points. So this is the digitized version. And we now define two functions, two digitized functions. One of them is v of t of n, and the other one is u. And if we look carefully, we can see that our response here, the profile, the desired profile, is actually a cross correlation between u and v. So this is this is something which is nice to realize, because if it is a cross correlation, of course we can implement it using FFT. So this is what we do. We implement the cross correlation in the frequency domain. We Fourier transform both of these functions, and then introduce inverse Fourier transform and obtain the desired profile. So this is one algorithm which can give us something which is more efficient than n squared complexity that we've seen previously. In this case, we need to do 3 Fourier transforms. But actually, there is even a better and more efficient approach. And to implement this approach, we express the exponential, one of the exponentials, we express them using the Jacobi angle expansion, and we use the Bessel coefficients Jn, and in this case I will save you the mathematics. We insert this expansion into the original expression, and we go through some derivations which I'm not going to focus on, and what we obtain eventually is an even more efficient manner to calculate the profile in the SFS OFDR, and it requires just 2 FFTs rather than 3 FFTs, as this expression here shows. So to summarize, OFDR can offer excellent sensitivity while maintaining high spatial resolution. Nonlinear scan adversely affect the spatial resolution, but accurate sinusoidal scans are easier to generate, and SFS OFDR is experimentally verified, and also we have verified, also experimentally, fast sinusoidal frequency scan OFDR, which offers high computational efficiency. So thank you very much.
Okay, let's thank Avishay for the presentation. Unfortunately, we cannot contact him right now, but we had the question for him and we have the answers. Just 3 answers, and the first one sounds this way. We have seen that you have mentioned SF scanning OFDR in 2015 for the first time, so today it is 5 years from the method demonstration in lab. What major changes have been done in recent years that help you to go towards the commercial instrument? And what did Avishay answer? The SFS OFDR deals with the limitation in OFDR, namely the non-linear scan. However, the OFDR have several other limitations. The main limitation is phase noise. During the years after the introduction and demonstration of the SFS OFDR, we have worked on topic of this noise, of this phase noise. The issues are how to model it and how characterize and how to mitigate it. But still, phase noise is a major issue which, as long as it not overcome, significantly limits the performance of OFDR and must be dealt with. Наверное, я должен перевести. Мы не можем, к сожалению, сейчас связаться с Авишеем для диалога в прямом эфире, но у нас есть несколько вопросов для него, и есть от него ответы на эти вопросы. И вот первый из них звучал как: вы упоминали технику OFDR еще в 2015 году, в первый раз за 5 лет после демонстрации в лабораторных условиях. Что изменилось, какие главные изменения произошли, что позволило этому двигаться в сторону коммерческого инструмента, коммерческого прибора? И ответ от Авишея был такой, что на самом деле нелинейное сканирование только лишь одна из проблем, а главное на самом деле фазовый нойз, фазовый шум. И все эти годы их команда работала над этой проблемой. Как это смоделировать, как это характеризовать, ну, естественно, потом устранить. И вот пока эта проблема не решена, довольно серьезные ограничения накладываются на сам OFDR. So the second question, you have demonstrated the way how the raw data could be shown as reflecting points at a conventional OFDR traces. Does the code unit that extracts the phase information for temperature strain sensing need the modification in the case of SFS? Вопрос заключается в том, что вот в данном докладе продемонстрировано, как исходные данные превращаются путем математических преобразований в типовую OFDR trace, ну то есть рефлектограмму частотной области. И задается вопрос, а какие, собственно, модификации программной части нужны для того, чтобы превратить эти данные по температурам и деформациям. And the answer for this question from Avishay. He says, actually not really. SFS gives us complex fiber backscattering profiles which can be processed similarly or maybe even identically as the profiles obtained from the regular OFDR or coherent OTDR. И Avishay отвечает, что вообще-то не совсем, что частотное сканирование дает комплексное преобразование профиля отражения таким же образом, как и делает это обычный OFDR-рефлектометр, и эти исходные данные могут быть обработаны как данные с любого OFDR или когерентного OTDR. And the third one is, could you please tell us why acoustic sensing is possible in the case of SF scanning? Третий вопрос звучит так. Не могли бы вы рассказать, как акустическое измерение возможно при помощи частотного сканирования? And the answer from Avishay. Acoustic sensing is obtained by taking sequential SFS OFDR profile measurements and extracting local phase variations that occur from the scan to the next. The phase variations corresponds to the acoustic signals at the fiber vicinity. Ну, ответ звучит приблизительно как то, что вот те данные, которые мы получаем описанным методом, мы получаем просто последовательно с каждого временного интервала и таким образом выстраиваем временной отклик, который является частотной характеристикой. Давайте двигаться дальше. Thank you. Let's continue. Do not hesitate to send your questions to OR2020@permsc.ru. If we didn't ask your question online, please know that we have emailed this to speaker directly and immediately. Thank you. Dear Avishay, thank you so much for your interesting presentation. We do hope to see you in Perm at our next conference. And the next speaker is Mr. Soma Sankaran. He is our conference partner from Denselight Semiconductors. His topic, end-to-end platform agnostic solutions for sensing and datacom. This talk is brought to you by Macro Group, our general partner.
Hello everyone, my name is Soma Sankaran, and today I'd like to talk to you about Denselight and our end-to-end platform agnostic solutions for both sensing and datacom. First, let me tell you a little bit about Denselight. We provide one-stop design and manufacturing of optoelectronic devices as well as integrated photonics solutions. We have over 100 committed and passionate people from 11 nationalities, and we are located at 2 sites, one in Singapore and the other in China. Our global R&D center is in Singapore. We serve 150 customers in 26 countries in the fields of telecommunication, biomedical, instrumentation, industrial, defense and security, as well as data center. We exploit our proprietary technology for hybrid integrated solutions. And most importantly, we have our own indium phosphide fab in Singapore. Denselight was founded in the year 2000 by a group of professors from a local university. We installed our first indium phosphide wafer fab in the year 2002 and came out with our first product in 2003, which was a Telcordia compliant SLED. In the year 2004, we came out with what we believe was the world's first G984 compliant GPON ONU transceiver. In the year 2006, we produced our first narrow line width laser, and we continue to sell this laser today into the wind LiDAR as well as the distributed acoustic sensing markets. Between the year 2008 and 2015, Denselight worked on a number of defense projects. This included DARPA in the US, as well as Singapore's DSO. In the year 2016, we were acquired by a public company, Poyet Technologies, headquartered in the US and listed on the Toronto Stock Exchange. Poyet at that time was developing their own photonic integrated solution, and they needed Denselight's expertise to develop optoelectronic devices that could be bonded onto these PICs. Poyet also brought in new local leadership in the year 2017, which then fueled Denselight's growth. In 2019, we established our second MOCVD and thereby increasing our wafer fabrication capacity. At the end of 2019, Poyet decided to spin off Denselight, and today we are an independent company with investments from private institutions. What's unique about Denselight is that we are vertically integrated. So we have R&D, we have wafer fabrication, we have packaging, and we have testing. We have both indium phosphide as well as gallium arsenide capability. And one of our core competencies is the indium phosphide to silicon photonics bonding capability. And this means we can produce optoelectronic devices that are flip chip enabled and have mode field adapters. And all this is done in our headquarters in Singapore, and Denselight also has an office in China. Today, our engineers have produced over 65 patents that enable us to deliver different solutions to both the sensing as well as the telecom markets. Fiber optic sensing has been Denselight's traditional market, and here one of our focuses is in test and measurements. We sell broadband SLED light sources into metrology, FPGA sensing, as well as components and material testing equipment. Our ELEDs are popular in the OCM markets, and we sell FP as well as DFB lasers into the OTDR market. Gas sensing, specifically methane, is a new focus for us where we sell our 1653.7 DFB lasers. Denselight also sells into the structural health monitoring market, where customers use our narrow line width lasers and our SLEDs, as well as SLED sets to deliver solutions. The medical market is an up-and-coming one for us, where we are able to customize chips for applications like continuous glucose monitoring. Denselight's solution for guidance and navigation, specifically fiber optic gyros, continues to grow, and today we are entering new markets like industrial robots and drones. We sell sleds and customize low DOP chips into this market. Lately, we are having discussions with customers on customized integrated solution that reduce size and cost in the FOG space. We sell our narrow linewidth lasers into the wind LiDAR market. This laser comes in a butterfly package, as well as in a plug-and-play integrated light module box that includes the laser and the driver. We are today working with automotive LiDAR customers to deliver light source and light amplification solutions for their silicon photonics-based platforms. We also sell our narrow linewidth lasers, especially the integrated light module, into the distributed acoustic sensing or DAS market, which includes perimeter security sensing. Over the last couple of years, Denselight has entered the datacom and telecom space with our indium phosphide chips. We sell 25G DML as well as high-power CW lasers into the PIC market, where we also have 25G and 50G pin solutions that can be bonded onto these PIC platforms. As you know, 5G implementation is gaining traction. Denselight has both CW lasers as well as 25G DML lasers, CTEM and ITEM, to meet the demands of this market. As data rates get higher, customers are looking at coherent transceivers to increase data throughput. Denselight is working with a number of customers to deliver gain chips as well as SOAs into this new market. And we play in the traditional markets, where customers use our laser chips to build TOs as well as TOSAs. The key takeaway from the last two slides is that Denselight can deliver platform-independent solutions, whether it is traditional sensing and datacom boxes or the new photonics integrated platforms. This is a busy slide, but what it does, it gives you an overview of our telecom and data center application solutions. We have solutions for data center networks, which include our high-power CW lasers, as well as our 25G DML lasers. We have solutions for local area networks that includes our 10G as well as our 25G lasers. And our lasers also go into the fiber access markets, both GPON and XGS-PON. We also have solutions, as I mentioned earlier, for the 5G front haul markets. So we cover a whole spectrum of the telecom and data center applications. As I mentioned earlier, Denselight can provide platform agnostic, or in other words, platform independent solutions. And this slide gives you a pictorial view of what these solutions are. Right on top, you have the traditional assembly into TOSA and ROSA or modules. Denselight can provide chips that go into these type of assemblies. And then you have some customers who use our lasers to assemble them into micro packages. And finally, right at the bottom, you have what's gaining popularity these days, which is really silicon photonics platform. And we have products that can be directly flip chipped onto these platforms. As I mentioned, Denselight is vertically integrated. We have our own chip design capability, and we grow all our chips in our fab in Singapore. This is why we are flexible and we can deliver solutions to different platforms. We do our own epi design and growth, as well as regrowth after grating writing. We have device fabrication capability, where we can do rich etch, dielectric passivation, isolation, contact metallization, lapping, and polishing. We have the capability to do spot size converters and the capability to enable flip chip bonding. And finally, we can do our own cleaving, HR and AR coating, as well as packaging. We have in-house burn-in and reliability, as well as accelerated live test equipment. All this enables us to deliver solutions from design to manufacturing. This slide shows you our product capability. We of course have, as I mentioned, the ability to grow our own chips, which includes DFB, FP, customized gain chips, customized sleds, as well as SOA. We can then take these chips and build into a few different types of modules, which includes the butterfly package, the TO can, as well as the TO pigtail. And then for some customers who are unable to design their own drivers, we can take these modules and build them into our plug-and-play integrated light modules that comes with the driver. Our wavelength range goes from 1270 nanometers to 690 nanometers, and we have powers that go from about 0.1 milliwatt to about 50 milliwatts. So, what makes Denselight different from some of the other players? Well, first of all, we have had a strong foundation. We have been in the market for about 20 years, and we were the first supplier to get SLED Telcordia qualification. We are one of the remaining few independent indium phosphide foundries, and we have the expertise to operate both R&D and manufacturing. We are a leading global manufacturer of sensing solutions, and today we are making a mark in the datacom and telecom fields. We have customers all over the world, in China, US, India, Japan, Europe, parts of Asia, as well as Russia. We have delivered strong growth in the last 3 years, and in fact, these were double-digit year-on-year growths. We can provide end-to-end manufacturing solutions, and our IP encompasses design, assembly, test, packaging, and box assembly. We have built strong relationships with many customers, and a number of them have been with us for many years. We strive to become a world-class company which can provide platform agnostic or platform independent solutions. We want to provide end-to-end, flexible, on-time customized solutions for customers so that they in turn can deliver game-changing products. And we are ready to capture many new market potentials in datacom, telecom, FOG, automotive LiDAR, DAS gas sensing, wind LiDAR, and instrumentation. In other words, Denselight wants to power your future through light. Thank you for listening. And if you have any questions, please don't hesitate to contact us.
Mr. Sankaran, thank you. Unfortunately, we continue our work in questions and answers in type in text mode. And again, we have time for 3 questions. First question is, does your company produce tunable lasers and frequency sweeping sources? Answer from Mr. Sankaran. We make photonic components that are used in ITLA. Maybe he means integrable tunable laser assembly, SOA, gain chip, and swept sources, SLED. The second question, it is possible to get SDK. SDK means maybe software development kit for your lasers to arrange the automation with programming tools like C#, LabVIEW, and others. And the answer? At the moment, we don't have SDKs for our products to these simulation tools. Of course, if customers have questions or need support, we have a team of engineers to help them. This is the answer for the second question. And the third question, could your device be customized? Say we need the diode with out of conventional datasheet parameters. Are you open for this? And the answer, since we are vertically integrated with our own fab, design team, and manufacturing, we can produce customized devices. We have done many customization projects, and that's one of our unique advantages. Наверное, стоит перевести. Первый вопрос у нас звучит так. Производит ли ваша компания источники с перестройкой по частоте? Ну вот, кстати, это перекликается с предыдущим докладом, здорово, да? Вот, и коллега отвечает, что мы делаем фотонные компоненты, которые используются в интегрируемых, перестраиваемых лазерных сборках, вот, и сканирующие источники. Второй вопрос звучит так. Возможно ли приобрести SDK, ну, то есть средства разработки для автоматизации программирования ваших устройств, для C#, LabVIEW и других сред? И ответ такой: к сожалению, SDK в данный момент не предоставляются, но если у потребителей есть вопросы, мы всегда готовы поддержать, и наши инженеры готовы им помочь. И вот третий вопрос, он перекликается со вторым. Вот можете ли вы производить так называемый custom shop, то есть какие-то специальные продукты, если они находятся за пределами типовых спецификаций? Открыты ли вы для такого взаимодействия? Вот, и отвечает господин Санкаран, что, как вы уже все знаете, мы вертикально устроенная компания, что у нас есть производство, разработчики, все это у нас присутствует, мы можем делать действительно кастомизированные такие устройства. Мы уже много такого кастом-шопа сделали для
разных наших партнеров, и в этом наше главное преимущество. Ну вот, наверное, так. Well, let's continue. Thank you. Давайте продолжать. Do not hesitate to send your questions to OR2020@permc.ru. If we didn't ask your question online, please know that we have emailed this to speaker directly and immediately. Thank you. Do not hesitate to send your questions to OR2020@permc.ru. If we didn't ask your question online, please know that we have emailed this to speaker directly and immediately. Thank you.
My friends, it is time for the invited talk. Please welcome Gilberto Brambilla. He is Professor Laboratory Head at Optoelectronics Research Center, University of Southampton, United Kingdom. His talk topic is in-house scattering optical fibres for next-generation distributed sensing.
Good afternoon. My name is Gilberto Brambilla, and I'm leading research on optical fiber sensors at the Optoelectronics Research Center in the United Kingdom. I also hold the second position at the Future Photonics Hub, where I'm Deputy Director and manage 25 researchers developing new technologies for improving manufacturing in the photonics environment. This follows my previous appointment as Director of the Center for Innovative Manufacturing Photonics, still in Southampton. My research group at the ORC has 15 researchers working on different aspects, from distributed to point optical fiber sensors, from femtosecond laser manufacturing to UV laser, from new spectrometers to optical fiber devices. Today, I will talk about our project on enhanced backscattering optical fibers for next-generation distributed sensing, which was carried out in conjunction with Dr. Martinez Beresna, Mr. Andrei Donko, and Dr. Ali Masudi. In my talk, I will start with a description of distributed optical fiber sensors, and will then propose the biggest issues faced by these sensors when operating at long distances. I will then move into a review of current proposed solutions and will focus on our solution that relies on the use of femtosecond laser writing to create a new generation of fibers with enhanced reflectivity. If you want to cover large areas or long distances with electronic sensors, you usually require numerous sensors. All of them are then connected with a data acquisition system through cables. The obvious consequence is that the complexity increases with the number of sensors, and the number of cables increases linearly with the number of sensors. In the case of distributed optical fiber sensors, all fiber sections are connected in series rather than in parallel, and the single source and detector are used for systems using up to 50 kilometers of fibers, which can be equivalent to 50,000 sensors. Distributed fiber sensing is extremely powerful, as it enables continuous real-time measurement of physical parameters, typically strain of temperature, along the whole entire length of the optical fiber cable. Optical fiber sensors rely on optical fiber backscattering for sensing, without any additional transducer in the optical path. Generally, a pulse of light is injected in the optical fiber, and each section of the fiber produces scattering. Some of the light is backscattered into the fiber and is brought back to the detection system, which produces the sensor response. As you can see in the bottom right graph, this is the typical trace recorded from the data acquisition system. There are three main types of scattering used in distributed sensing: Raylight, Brillouin, and Raman. Rayleigh backscattered radiation has the same wavelength as the forward-propagating radiation and is produced by intrinsic inhomogeneities of the glass, which are always present in optical fibers, and are due to thermal fluctuations within the fiber during the cooling of the fiber on the drawing tower. Brillouin backscattering radiation in silica fibers is shifted by approximately 11 GHz. Brillouin scattering is attributed to the formation of temporary acoustic gratings induced by the propagation of light pulses within the glass medium. Finally, Raman scattering is shifted by approximately 13 THz. Raman scattering is given by the inelastic scattering of incident photons on the silica network. During each scattering, there is energy exchange between the photon and the silicon-oxygen phonon, which results in the large energy shift. For both Brillouin and Raman scattering, the frequency shift can be negative when the photon loses energy, and the shift is called Stokes shift, or positive when the photon gains energy from the silica, and the process is called antistokes. Once the light is generated, there are three main architectures that are used for distributed optical fiber sensing. The most common is called Optical Time Domain Reflectometry. In this architecture, a laser source generates a light pulse, either through direct modulation or external modulation, and the pulse is then injected into an optical fiber through a circulator. Backscatter light goes through the circulator, is amplified, filtered, and then is collected by a detector. In this architecture, the source frequency is locked. The distance at which the measurement is carried out is provided by the time of flight. Light takes longer to travel to further positions. Thus, the backscatter radiation will be collected at a later time by the detector. An alternative approach is called optical frequency domain reflectometry. In this technique, the laser source frequency is repeatedly scanned across a frequency range, and the emitted radiation is split in two parts by a coupler. One part is delivered to the fiber under test through a circulator, while the other goes directly to the detector. The backscatter radiation goes through the circulator and is recombined with the light coming directly from the laser, and the detector monitors the interference between the two. This technique usually allows for better spatial resolution than OTDR, but only over a short distance. A more complex architecture is represented by the optical correlation domain analysis, or CDA, where the laser signal is modulated at radio frequency, and the fiber under test is accessed from both sides. By controlling the probe and pump pulses injected into the fiber, it is possible to pinpoint the specific position analyzed that generates the. In our recent research, we have focused on distributed acoustic sensing, or DAS, using phase OTDR. Basically, the sensing architecture monitors dynamically the phase difference between two separate points along the fiber, and which are here represented by the red and green sections, and tracks them along the time. In its simplest description, a pulse of light is injected into the fiber, and the reflection at the 2 points, here represented in red and green, provide 2 different back-reflected pulses that are made to interact at the detector. If they are completely in phase, the measured intensity will be maximized. When the fiber is stretched, the 2 points that back reflect the radiation are further apart, and the 2 back reflected pulses now interact with a different phase, resulting overall in a smaller total intensity. It's interesting to note that the phase change is linear with the elongation, meaning that it is possible to quantify the amplitude of the dynamic elongation. In other words, it is possible to quantify the acoustic field. The architecture that we use can be divided in 3 parts: source, fiber under test, and detector. In the source, we have a laser, which is directly modulated by a pulse generator. An isolator is used to avoid back reflection into the source that might alter the source stability. Pulses are then amplified by an erbium-doped fiber amplifier, and the filter is then placed online to remove any unwanted amplified spontaneous emission. After passing through a circulator, the amplified pulses reach the fiber under test. This is typically in the region of 50 kilometers long, and in the lab only a small section is perturbed, typically using a PZT to simulate vibrations. On the contrary, field measurements experience vibrations and therefore provide information along the whole length of the fiber. In the fiber, light is scattered, and a portion of the backscattered light is then collected into the fiber itself and delivered to the detection system after passing through the circulator. The detection system consists of an erbium-doped fiber amplifier, which boosts the backscattered signal, followed by a Bragg grating, which removes any unwanted amplified spontaneous emission. The amplified backscattered pulses are then split by a coupler into 2 branches, one which has a delay line that determines the sensor gauge length, and then passes through a 3-port coupler to reach the 3 separate detectors. In our setup, we used 3 detectors to have always a strong signal and avoid signal fading. The detectors are then connected to an oscilloscope, and the time dependence is monitored and recorded. And this provides the final time dependence that is presented in a typical curve like this one. There is a problem though. Although the sections of fiber close to the laser provide a strong backscattered signal, sections far away produce a very small signal, which becomes comparable to the system noise. In other words, the system suffers from poor signal-to-noise levels at distances in excess of 45 kilometers. This is the reason that the system has two amplifiers. One to increase the intensity of the pulse launched into the fiber, and the other one to increase the intensity of the backscattered signal. Several solutions have been proposed in the past to increase the signal level of the backscatter radiation. In 2013, Sasha Lear and colleagues proposed to produce voids into plastic optical fibers by focusing femtosecond laser pulses into a polymeric fiber. As you can see from the top left image, different pulse energies provide different void sizes, and therefore different backscattered intensities. The picture on the right shows the effect of a dozen scattering points inscribed into a polymer optical fiber when a red light was launched from a fault finder. The voids produce a massive scattering, which can be easily seen by bare eye. The issue is that only meter-long sections have been fabricated, and all samples exhibit huge losses, typically well above 1 dB per meter. A second technique, proposed by Loranger and colleagues, relied on the process of hydrogenation of optical fibers. Hydrogenation is typically used to enhance the photorefractivity of optical fibers in short lengths. Grating writing is usually associated with the exposure of the hydrogen-loaded fiber to a sinusoidal light field, which changes the refractive index in a periodic way. By exposing the whole fiber, Loranger and colleagues noticed that backscattering was enhanced. Although this process allowed for an increased signal, it was also associated with an equally increased loss, meaning that no significant benefit was identified with respect to conventional telecom fibers, which are significantly cheaper and do not require any expensive hydrogenation process. A third solution, proposed by Thevenards and colleagues, was called faint long gratings, or flogs. These were very weak gratings, written along the whole length of fiber. Grating are wavelength encoded, meaning that a change in temperature along the fiber length results in a wavelength shift in the recorded spectrum, as shown in the right figure. The frequency detuning is proportional to the temperature change or to the fiber elongation. Thus, it is possible to measure quantitatively the temperature or strain along the fiber by monitoring the frequency shift. Unfortunately, this technique is challenging to implement over long lengths of fiber, and only meter-of-long samples have been made. On top of it, this technique is very expensive. A fourth solution is represented by fiber break gratings written into the fiber within ultraviolet lasers during manufacturing on the drawing tower. The bare fiber is exposed to pulses that inscribe a grating, and then it is coated. The resulting fiber has the same mechanical performance of conventional telecom fibers, but has gratings that enhance reflectivity at selected wavelength by 30 to 40 dBs. Unfortunately, also loss is increased to values of the order of 10 dBs per kilometer, meaning that effectively the range of OTDR sensors is extended by approximately 4 kilometers. This solution is available commercially. A fifth approach used enhanced scattering fibers, where weak break ratings were continuously written into a telecom fiber using a femtosecond laser. This approach produced fibers with smaller losses, typically of the order of 0.7 dB per kilometer, with a signal enhancement of 17 dBs. This resulted in a range extension of approximately 24 kilometers. Like the previous approach with the fiber break rating fibers, this approach suffers from wavelength encoding, meaning that these fibers operate only within a limited range of wavelengths, or, in other words, temperatures or strains. The sensing dynamic range is limited by the grating reflectivity bandwidth. In our approach, we used femtosecond lasers to modify the fiber properties. In this figure, you can see the setup we used to manufacture the fiber. Pulses from a femtosecond laser at 1030 nanometers went through a beam telescope and then a BBO crystal that was used to frequency double to the green. The resulting polarized light was then focused through an objective lens into the fiber. Typically, femtosecond lasers deliver pulses in the range 100 to 500 femtosecond laser duration, with nanojoules energy, and produce refractive index changes of the order of 10 to the minus 3 up to 10 to the minus 1 in silica. The interaction between femtosecond laser pulses produce a variety of effects, but are mostly related to carrier excitation and relaxed thermalization. No significant thermal effect is observed. Thermal and structural events, such as thermal diffusion or resolidification, are typically observed with longer pulses, nanosecond pulses. As shown in the figure on the right, femtosecond pulses are usually absorbed by silica through multiphoton absorption and produce quantum tunneling that induces avalanche ionization and a refractive index change limited within the focal point of the beam. Different writing conditions can produce different effects in glasses. As you can see in the figure on the left, the right writing conditions can provide a smooth refractive index change, which is often exploited to write optical waveguides in bulk glasses. At high intensity, as shown at the bottom right, it is possible to generate voids within glasses. Laser pulses deliver high energy into a small volume, producing micro-explosions that turn the material into plasma with very low density. The material then solidifies, leaving a void at the center of the focus beam. At the specific pulse duration and energies, it is possible to generate microgratings on the top right, with smaller pitch than the incident wavelength. These are extremely interesting structures that result in an unusual scattering. In our experiments, we wrought reflectors using a femtosecond laser manufactured by Light Conversion in Lithuania, with an average power of 1 watt, delivering pulses of approximately 200 nanoseconds duration. The laser central wavelength was frequency doubled to 532 nanometers. We produced 81 meters of fibers with reflectors and spliced it at the end of 50 kilometers of telecom fiber. The OFDR that was used to make this measurement delivered pulses with 1 watt peak power at 1550 nanometer. As you can see from the trace reported here, there is an increase in the back reflected signal, which is about 2 orders of magnitude larger than the Rayleigh background noise. We measured the induced loss by using the so-called cutback method, conventionally used in optical fiber manufacturing to measure loss. We produced 2 different samples of fibers with 300 and 400 reflectors respectively. The samples were shortened by removing 100 reflectors at a time. As you can see from the graph on the right, the intensity decreases less than 1% over the investigated section, leading to an overall loss smaller than 0.1 dB per kilometer for applications using OFDR with 1 nanosecond pulses. When we repeated the same measurements with a fiber with 400 reflectors, we achieved a loss that is very, very similar, and to some extent even smaller. As standard telecom fibers have a loss smaller than 0.2 dB per kilometer, the total loss of a standard telecom fiber with inscribed reflectors is smaller than 0.3 dB per kilometer, and the back reflection enhancement of 20 dB implies an overall extension of the detection range by 66 kilometers round trip, or 33 kilometers if we consider a single end access. In conclusion, we have developed a novel fiber with enhanced backscattering for OTDR distributed optical fiber sensing. The fiber was manufactured using a femtosecond laser to structure telecom optical fibers and increase back reflection by 20 dBs. The loss increase is smaller than the intrinsic fibers and has been evaluated to be smaller than 0.1 dB per kilometer. This could extend sensing systems by 66 kilometers, or 33 kilometers if we consider single access, without the need of amplification. Thank you very much for your attention.
Okay, let's thank Gilberto for his presentation. Unfortunately, he is not here too, and we are going to read the questions and the answers for Gilberto. Well, the first question sounds this way. Are there some ways of improving backscattering at the chemical deposition stage in fiber? And the answer from Gilberto is yes, they are. By choosing compositions to increase density fluctuations in the core, it is possible to enhance band scattering. The issue here is to maintain low loss, as increased backscattering along the whole fiber is usually associated with a loss larger than 1 dB per kilometer. Вопрос заключался в том, возможно ли создание улучшенных параметров обратного рассеяния в волокне на стадии осаждения реагентов. Ответ был да, возможно, подбирая соответствующие композиции материалов, мы можем увеличить плотность флуктуаций в сердцевине, и да, действительно, таким образом можно улучшить обратное рассеяние. Но проблема заключается в том, что мы увеличим и потери в будущем волокне таким образом, а это затруднит использование его в системах, когда затухание составляет более 1 дБ на километр. Well, the second question is, at the slides you show the results of writing gratings in different materials, say borosilicate and fluoride glasses. Does this means that you also tested these for panda type fibers? And the answer from Gilberto sounds this way. We have not tested panda fibers, at least not in length suitable for distributed sensing. The evidence we have gathered so far points to the possibility to increase backscattering in panda fibers too, as our post-processing can be accurately focused in the core only. Вопрос заключался в том, что на слайде показаны некоторые материалы, в которые записывали бреговские решетки, в том числе те материалы, которые используются при изготовлении волокон типа панды. И вот был вопрос, а как действительно испытывали ли волокна панда в дальнейшем? Ответ был таким, что так, чтобы на 100% нет, по крайней мере на тех протяженностях, которые позволяют назвать эти системы распределенными. Ну а в целом тот опыт, который у них есть, говорит о возможности увеличения обратного рассеяния в волокнах типа панда, поскольку они в целом сфокусированы все на сердцевине, и тут нет ничего противоестественного для их методики. Well, and the third question is, how do you think, is this possible to achieve some backscattering light enhancements using conical core fibers? Yes, I think there is the possibility to increase backscattering, says Gilberto, with diameter changing fibers, but this effect, first, should be significantly smaller than what we have achieved, and the second point perturbs the forward propagation to increasing the overall propagation loss. Вопрос звучал так: могут ли волокна с конической сердцевиной каким-то образом быть полезны в улучшении характеристик параметров обратного рассеяния? Ответ был да. Возможность такая есть, когда речь идет о таких волокнах, но этот эффект будет существенно меньше, чем получили они, используя свою технику. И второй момент, надо принимать во внимание то, что потери будут увеличены в прямом прохождении, и это суммарно отразится на итоговых потерях, которые придут на фотоприемник, который детектирует обратное рассеяние. Okay, Gilberto, thanks again, and we are going to continue. Do not hesitate to send your questions to OR2020@permsc.ru. If we didn't ask your question online, please know that we have emailed this to speaker directly and immediately. Thank you. Want to get the amplified spontaneous emission C-band source for free? Macro Group invites participants to fill out a questionnaire before 2 p.m. plus 5 GMT on September 24th, following the link you have in the conference shadow or attached to this stream. On September 24th, Macro Group will place the amplified spontaneous emission source of C-band by Denselight Semiconductors among the participants who have filled out the questionnaire. The draw will be randomized and the winner will be selected live. Using the contacts given by the participants in the questionnaire, Macro Group will contact the winner to clarify the details of sending the prize. Thank you.
Well, get ready for the next interesting paper. This is about the reflectometer for measuring losses in small-length optical fibers based on the registration of low-frequency Raman scattering.
Today I am going to make a report about reflectometer for optical losses measurements in short length of optical fiber by registration of the low-frequency Raman scattering of light. Time-domain reflectometers are intended for evaluating transmission losses in optical fiber and have become very customary in building optical communication links. Their characteristics are usually quite consistent with practical needs, but there are some problems of measuring attenuation of light in length down to tens of meters of optical fiber with high accuracy. There is also a problem to measure attenuation of optical fiber segment right after fiber connection because of reflection on the joint of connectors. The accuracy of optical measurements in single-mode fiber with reflectometer based on relays backscattering recording is limited for two main reasons. One of them is residual polarization sensitivity of the real reflectometric design. The other reason is that the use of relay scattering always results in noise-like reflectograms because of frozen backscatter coefficient fluctuation, which cannot be eliminated by signal accumulation, is higher at a smaller width of the light source spectrum. Far less noisy reflectograms can in principle be obtained by measuring the power of Stokes or anti-Stokes scattering lines. However, both lines in question lie beyond the C-band, which may be unacceptable. We propose for the first time obtaining reflectograms at the frequencies of boson peaks in Raman scattering. The figure presents the Raman spectrum of silica glass fiber. Curves 1 and 2 refer to Stokes and anti-Stokes Raman, and curves 2, 3, 4 to Stokes and anti-Stokes boson peaks. The frequency shift of the boson peaks is about 100 per centimeter, which corresponds to a wavelength shift of the order of 10 nanometers in the C-band. Figure 2 shows a schematic of the experimental setup for time-domain reflectometry. A distributed feedback laser diode driver emitting at 1551 nanometers with a bandwidth within 1 nanometer generates 40 nanosecond pulses. After an erbium-doped fiber amplifier, the probe light passes through a narrowband filter with a passband under 100 GHz to exclude the contribution of luminescence in the amplifier to the reflectogram. After passing through a polarization scrambler and circulator, the probe light enters test fiber. The peak power of the probe light is 1 watt, was limited to avoid nonlinear effects distorting reflectograms. The backscattered light passes through the circulator filters and a switch and enters a photodetector photodiode with a trans impedance amplifier. Filter covered yellow with passband 6 nanometers reject the relay scattering. Filter red suppresses both the Stokes and anti-Stokes Raman signal, but transmits the boson peak. The signal from the photodetector output is amplified, digitized by an analog-to-digital converter, and fed to a computer. On the first plot, the emission spectrum at the photodetector input is shown. Second plot shows a reflectogram of a 1000 meter length of Fujikura future guide low water peak fiber showed on curve 1. The reflectogram was obtained via signal acquisition for 40 seconds using an ADC with a clock frequency of 100 MHz. The spatial resolution of the reflectometer was estimated at 5 meters. The left axis represents the original signal as recorded by the ADC. The right axis corresponds to representation utilized in conventional reflectometers, where passes of light in two directions, forward and backward, are taken into account. This axis is commonly used to represent optical loss. The reflectogram has an extremely low noise level. Curves 2 and 3 obtained for the same fiber segment using a commercial reflectometer with polarization scrambler and without it. The spatial resolution is estimated at 10 meters. It is also clearly demonstrated that conventional reflectometers cannot accurately determine attenuation at the length of tens and hundreds meters. On this slide, the first figure shows attenuation in the fiber as a function of the measurement section length. It is seen that even at a fiber length as short as 50 meters, the measurement error does not exceed 2,000 decibels per kilometer, with 0.189 decibels per kilometer taken to be true value. Second figure shows the random error in attenuation measurements as a function of fiber section length. The non-monotonic behavior of the curve in this figure is due to insufficient measurement sensitivity. The intensity of spontaneous scattering by phonons is temperature dependent, unlike in the case of relay scattering. In particular, the temperature coefficient of scattering intensity for boson peaks in Raman scattering is about 3000 Kelvin minus 1. The intensity of spontaneous scattering by phonons is temperature dependent, unlike in the case of relay scattering. In particular, the temperature coefficient of scattering intensity for boson peaks in Raman scattering is about 3000 per Kelvin. The higher the required measurement accuracy, the more stringent requirements should be placed on the temperature ununiformity in the subject of the measurement. If it is a spooled fiber optic cable, sufficient ununiformity is difficult to ensure in a number of cases. One possible solution is to additionally measure the anti-Stokes Raman signal, which has the temperature coefficient about 8,000 per Kelvin. To demonstrate possibilities of compensation for a non-uniform temperature profile along the fiber length, a 1,000-meter-long fiber coil was heated non-uniformly, with deviations from the average temperature of up to 3 Kelvin. In practice, such deviations are unacceptable. As a result, the reflectogram of the boson peaks in Raman scattering took the form shown in Figure 1. A joint analysis of the reflectogram with one obtained for the anti-Stokes Raman signal allowed us to obtain the resultant plot for optical losses in Figure 2, which demonstrates that temperature errors were eliminated for the most part. However, the noise level increased by 6 to 7 times. It seems likely that refining the compensation algorithm can improve the result. With the use of a bosonic-based reflectometer, there are no dead zones after connectors, which is important in studies of relatively short length of fiber. The figure shows a reflectogram of two fiber segments connected by different types of FC-UPC connectors. It is seen that reflection has a very weak effect on the reflectogram. Spatial resolution can be estimated at 2 meters at a probe pulse duration of 20 nanoseconds, and there is no dead zone after the connection. In conclusion, it should be said that a reflectometer scheme for light attenuation management in optical fiber using boson peaks in Raman scattering has been proposed and studied experimentally for the first time. Eliminating interference effects related to the use of relay scattering, we have achieved high accuracy in attenuation measurements in short fiber segments from 50 to 1000 meters. A decrease in noise by more than 30 times has been demonstrated. Such measurements are performed within the C-band. A drawback to the scheme is that Raman scattering intensity is temperature dependent. An approach has been proposed that ensures a temperature compensation for the related errors by additionally obtaining a reflectogram at the wavelength of anti-Stokes Raman signal whose intensity is a strong function of temperature. Thank you for your attention.
Do not hesitate to send your questions to or2020@permc.ru. If we didn't ask your question online, please know that we have emailed this to speaker directly and immediately. Thank you.
We thank our industrial partner, Perm Scientific Industrial Instrument Making Company, PNPPK. PNPPK is the organizer of photonics cluster in the city of Perm. Great! We are about to hear another talk. It is titled Evolution of Temperatures and Strains, Discrimination Possibilities in Data Obtained by the PBOTDA Method. The full text in English and Russian is also available in Instrument and Experimental Techniques journal.
Hello, my name is Fedor Barkov. I'm member of Photonics Lab of Penn Federal Research Center, and I'll talk about our investigations of possibility to measure temperature and strain simultaneously using polarization Brownian reflectometry in anisotropic optical fibers. There is a number of tasks where it's necessary to perform distributed measurements of temperature and strain simultaneously. Among them are examining fiber optics gyroscope performance, studying U-shaped memory materials, testing aircraft components, and so on. We know a lot of already existing techniques to discriminate temperature and strain using optical fiber sensors. Some of them are presented on this slide. Basically, typical parameters of such systems are following. Temperature measurement accuracy is of the order of 1 Kelvin, and strain measurement accuracy is of the order of several microstrains. Of a special interest to us is the idea to use two axes of polarization maintaining fiber as two independent sources of signal. For example, when examining performance of fiber optics gyroscope, everything is already installed, including polarization maintaining fiber Panda. And all we need to do is to measure Brownian frequency shifts into axes and recalculate them into values of temperature and strain. Basically, Brownian frequency shift depends on both temperature and strain, and considering two axes of polarization maintaining fiber not being equal to each other, we can write the dependence in matrix form. Here, column in the left side of the equation consists of two Brownian frequency shifts. Column in the right part consists of two measured quantities, and matrix coefficients are simply partial derivatives. Necessary and sufficient condition to recalculate measured Brownian frequency shifts into required values is non-degeneracy of matrix A. As it's clear, there could be potential problems with such a recalculation. At first, we never know the exact values of the matrix. And secondly, the measured values of Brownian frequency shifts could differ from real ones. All this could lead to errors in determining temperature and strain values. The main question of the presented study is following: whether it's possible to use standard Brownian reflectometer and to obtain results comparable with other techniques. Since the technique must be extremely sensitive to non-degeneracy of matrix A, we started from calibration experiments. Using thermal chamber, we obtained dependencies of Brownian frequency shifts on temperature for both axes. You see that they look quite similar to each other, but still they are not the same. Another experiment was to stretch the fiber at room temperature. It gave us two missing coefficients of the matrix. We used the obtained coefficients for further analysis. There is one important thing to mention. The dependencies are quite linear. It means that partial derivatives can be obtained with very good accuracy. Regression analysis shows that the error in determining matrix coefficients is less than 1%. The first thing we studied was the influence of calibration errors on measurement errors. We produced a number of numerical simulations by the algorithm shown on the slide. We set temperature and strain values, calculated Brownian frequency shifts for two axes, distorted one of the matrix coefficients, recalculated Brownian frequency shifts values to temperature and strain using distorted matrix, and found the discrepancy between given and calculated values. And the results are given on the next slide. You can see that 1% calibration error doesn't have to lead to significant measurement errors. The next step was to investigate how error in measuring Brownian frequency shift affects the results of temperature and strain determination. In order to do it, we performed another series of numerical simulations. The algorithm is given on the current slide. We modeled Lorentzian spectrum, added some noise component, discretized obtained spectrum, and looked for the maximum value in it. Analogous procedure was performed for the other fiber axis. Having obtained two measured brilliant frequency shifts, we recalculated them into temperature and strain. And the results of the simulation are given on the next slide. Shown here is the dependence of measurement error of temperature in kelvins on the frequency scanning step for different signal-to-noise ratios. Two conclusions can be made. The first conclusion is that at low signal-to-noise ratio, the error is mainly determined by signal-to-noise ratio itself and doesn't depend significantly on frequency scanning step. And the second conclusion is that even scanning to noise ratio is high enough, say above 100, there exists a region where it's possible to get suitable results. But in order to do it, one has to have small enough frequency scanning step, less than 1 MHz. By suitable result, I mean of course that the error must be comparable to other techniques. It must not exceed 1 Kelvin. Here you can see the demonstration how the method works when two criteria are satisfied. We set some arbitrary distributions of temperature and strain, modeled the measurement procedure, and compared the results. You see that they are pretty close to each other. Then we proceeded to the experiments. The schematic is given on the current slide. We used 20 meters long under fiber. First 5 meters were so-called free winding, and the rest of the fiber was wound on a solid aluminum cylinder. Then the construction was placed in a thermal chamber. One could expect that with temperature increase, first 5 meters would experience only thermal influence, and the rest of the fiber would be subject to both temperature and strain. Signal-to-noise ratio was estimated using single spectrum processing and was found to be equal to 10. Frequency scanning step was set to 5 MHz. So both parameters didn't satisfy the obtained criteria. The obtained results for the temperature are presented on the current slide. In an ideal case, we would have the set of horizontal lines. In reality, it's more or less the case for the part of the graph, say from 4 to 6 and from 14 to 16 meters. On the rest of the graph, there are regions where given and measured values correlate in some respect, but there is no quantitative agreement at all. Were it be due to the noise, these regions would change from one curve to another, but their positions are the same for all the temperatures. Maybe it's because fiber in these regions differ from the rest of the fiber, and matrix coefficients are not the same. The analogous picture we have with strain determining. Qualitatively, it looks not bad. There is clear difference between free winding region and the rest of the graph, and with temperature increase, strains become larger, as one could expect. Still, there are regions which differ significantly for no obvious reason. Thus, the experiment demonstrates the indicator level sensing. I mean that one can see the changes in temperature and strain, but one cannot trust the exact obtained values. Summarizing, we have investigated how different factors affect the accuracy of temperature and strain discrimination by measuring brilliant frequency shifts into axes of polarization maintaining fiber. Errors in determining matrix coefficients don't have to lead to significant errors. Signal-to-noise ratio must be high enough and frequency scanning step must be small enough to get temperature error not exceeding 1 degree. The last thing to be mentioned is that finding maximum approach is definitely not the best way to obtain brilliant frequency shift. Even in the absence of noise, it would give the error of quarter of the frequency scanning step due to discretization. Modern algorithms like Lorentz and fitting should give much better results. So in reality, requirements for the signal-to-noise ratio and frequency scanning step might be not so strict. It's the subject of our future study. Thank you for your attention, and if you have questions, please address them to the email shown on the slide.
Большое спасибо Федору Леонидовичу. Это была видеопрезентация, присланная в оргкомитет. Мы ее с вами только что просмотрели. К сожалению, Федор Леонидович не может сейчас ответить на наши вопросы по техническим причинам. Но на правах соавтора эту обязанность возьму я. И сейчас зачитаю то, что нужно спросить. Так, первый вопрос у нас есть. Каковым, по-вашему, может быть применение метода с такой точностью? Ну, применение метода, как это следует ожидать, наверное, какая-то индикаторная характеристика того, что должно или не должно в целом меняться. Допустим, идет процесс, где мы измеряем температуры, и резкое появление деформации может привести к пороговому выключению системы. И это появление деформации, допустим, нужно отследить. Вот. Ну, а в целом мы, конечно, хотим уходить из индикаторных применений в сторону метрологии, применять новые методы, там, Лоренцов фитинг, метод обратной корреляции и другие методы. Так, в чем сложность сделать более точное разделение с помощью динамической решетки Брега? Сложности нет. Есть просто задача изначально, которая сводилась к тому, что нужно получить результат на существующих типовых установках, утвержденных для метрологических каких-то процессов. Вот. А на самом деле, да, динамические решетки Брега здесь тоже применимы. Так, можно ли как-то повысить качество разделения, используя эту же аппаратную часть? Ну, вот как было уже сказано в первом ответе, да, это метод обработки сигнала, то есть определять максимум, как Федор Леонидович сказал, по процедуре FindMax. Это достаточно устаревшая вещь. Вот. Ну и методы другие, там обратная корреляция, которые мы уже описывали и хотим применить для разделения температуры и деформации. Все будет тоже сделано. Так, нужно перевести. I need to translate this. Yes. Well, the first question was how do you see the possible application? And the answer was we see it in the indicator-like application now to see if the temperature or strain changes, if one of these ones shouldn't. In future, after applying of motor spectral processing techniques like Lorentz and fitting, backward calculation, and so on, we hope to improve it. The second question was why do you see that using of dynamic Bragg ratings is a problem? And the answer was no, it's not a problem. The general idea was to use the typical and well-known maintenance for this, and that's it. The third question, do you have any ideas of improving discrimination software? Sure, it was mentioned above, Lorentz and fitting, backward correlation and other methods. Thank you. Спасибо.